Hello again. For those who don't know me, my name is Ben Polzine. I'm a former petroleum engineer turned data scientist, and lately I've been falling in love with deep learning specifically. I'm currently pursuing my TensorFlow professional certification and wanted to take a chance to dive into one of my computer vision projects that I've been working on. I do have a more extensive introduction on a prior video if you'd like to take a look at that, and it also introduces the hello world of computer vision. But for this one, I'd like to focus on this great project. It has an all-encompassing workflow, starting with a lot of data pre-processing, some data augmentation, regularization techniques, really tuning the model, and then using it to apply some predictions in the end. So it's a really great example, again, of the entire computer vision workflow. And it utilizes the CIFAR10 dataset, which is one of the most popular datasets in machine learning research. Again, very robust dataset, 60,000 images from 10 different classes. So we'll dive right in. I did utilize the Keras workflow for this project. Brought in a lot of these functions just to help clean up the code. And so we'll see the impact of that later on. But yeah, we'll go ahead and get started here. Load in the data set, take a look at what we've got. We've got some small, low-resolution images, but some great data to work with. Various automobiles, animals, but more specifically, horses, cats, dogs. Really good challenge for this model to really be able to distinguish between these classes. So do some one-hot encoding on our label set. As mentioned, build a modular code so that make this process really efficient as we go through, as we turn those different knobs, add different regularization techniques. Makes it easy to evaluate these different models in different ways if we have the code modularized. And so bring it all together in what we call a test harness and get started. Computer vision, one of the most powerful networks is the convolutional neural network. What this does is it creates these convolutional layers which are able to scan through the image and do what's called feature extraction. And so that finds the hard lines, the vertical lines, the horizontal lines, but also the changes in colors and just the various features of an image that can be used to classify these different classes, which then feeds into a deep learning fully connected layers in output and then the output layer. And so I did choose to use the VGG16 architecture as my foundation. It's a great building block, very easy to implement, very powerful. One of the classics for computer vision. It does utilize multiple convolutional layers for each max pooling layer. So we'll go ahead and dive right in. And so we have our first model, again, just a simple VGG16 model. Achieved a pretty good test accuracy, 74%. That's fine for a baseline, but looking at our curves, we can see that there's a lot of room for improvement here. This divergence in the loss function is really not good and clear signs of overfitting. Definite room for improvement. And I want to start with just some simple regularization. For a deep learning model like this, dropout regularization is very effective. What it does is at random, it'll drop out whatever you choose. And for this one, we'll just do 20%. And so it'll eliminate 20% of the nodes of each layer at random, which will prevent it from getting too biased and too focused on any individual features that the model is learning. And that led to a really great increase. Jumped up the accuracy to 83%, improved the curves a lot. Skip over that. But we have data augmentation, which is a really powerful pre-processing technique in computer vision. What it does is creates a lot of synthetic data to expand your data set, either slightly rotating an image, zooming, cropping, to really give your model a lot more data to train off of and really improve its performance. And again, similar to the regularization, a really significant performance. So if we combine those two techniques, the regularization and the data augmentation, and allow our model to keep training even longer, it should really, really improve. And as we can see, we end up with a great model, 88%, really performing well. We can use that to build a simple test function to run new examples of different images, bring in test data that it's never seen before, and get our results and see. We're able to identify the airplane, able to identify an automobile. So we've got a great model here. We did use the stochastic gradient descent for optimizers, so it's definitely worth taking a look at the Atom optimizer, which is a dynamic optimizer, and it performed even better, almost 90%. So here's our summary. Please check out this code if you'd like, and look forward to